To you, designers and engineers, captains of industry, and leaders of thought, anyone whose ambitions have ever exceeded what was possible, this is your moment. Your rewrite history, the world is not flat moment. Every facet of how you design and manufacture is about to be reinvented, and it all starts here. With the smallest of building blocks, the mighty HP Voxel. You and it are about to change the world by advancing radical prototyping, accelerating manufacturing, and taking precision and strength to unheard of heights. From today forward, the 3D printer is a factory for thought, where the things we make will make us smarter, better, more human. What a future we'll create with new materials and embedded intelligence. Together, we'll bring extraordinary to the everyday and reality to dreams light years away. Welcome to the age of digital production, on demand, a world without waste, without inventory, without warehouses. Meet the first HP Jet Fusion 3D printers, the digital furnaces of the next industrial revolution. Join us as we engineer the never-before Voxel by Voxel. HP Multi-Jet Fusion. Keep reinventing.
Okay. Sorry, I probably should have called everybody back, but I figured getting the video would get everyone's attention to talk about going into our next session here. And hopefully that video gave you an idea of the future. And so what we want to do is we're gonna change, and we're going to go into our next topic, which we call the next industrial revolution. And that video gave you a little bit of framing, but let me breathe some life into it, and then we're going to welcome up a couple folks to talk about exactly what we see as that next industrial revolution. So this is an interesting term that gets coined and gets used in a very loose way in many ways. But I want to breathe some life into it and talk about a real revolution. For the last 150 years, we have built a $12 trillion economy on a very simple manufacturing model. And that simple model is, I take raw materials, I stage them in at the appropriate time. You can even back up one. I design something, and I tend to design those in either mature markets or area of concentration where there's technologists, there's designers who know how to put something together. And then I take that item and I put it somewhere to be manufactured in a low-cost or highly automated environment. I stage raw materials in, I figure out how to manufacture or how to create something in a low-cost automated way, and then on the back end, I figure out how to store it in a retail center, a distribution center. I figure out how to manage a channel all the way from where it left the factory in. And I distribute those products all the way around the world. So to draw the whole picture together, I design in one place, I ship it somewhere to be manufactured, I load it on boats, and I ship it around the world to be in the right place at the right time. Just that activity of shipping it around the world, of relocating it, takes about 5% of our world's oil supply. Just moving the products that we consume. Now, and it doesn't matter whether you're doing Twinkies, tablets, Toyotas. Our entire economy is built upon this model of the Industrial Revolution. And what I'm going to tell you is that over the next 30 years, to address the biggest issues that we see in mankind, when we see densification and move to urban environments, we see hyperglobalization, I'm here to tell you that over the next 30 years, that model will be turned on its head. And what we're going to do is to go into a model that is full digital manufacturing. Now, what do I mean by that? So that industrial revolution of today, that is what we call analog manufacturing. What's upon us today, and what you see with the advent of 3D printing and the ability to do it, is what we call additive manufacturing. And that's when now I can go from a digital representation instantly to a part through a push of a button. But all I'm doing is building up something from a base to assemble it. But the next wave is what we call digital manufacturing. And in digital manufacturing, every object can be represented in an algorithm, in a methodology that describes that part down to a voxel level. Now you saw a little video we opened it around voxel. Voxel is a simple idea. Today we have pixels. They're the things that create the images on the screen. But when you move that into a 3D space and you have a physical object, that is represented by a volumetric pixel or a voxel. And then that can describe everything about a part itself. So in the next 30 years, what we see is a world in which I describe the parts at a voxel level, everything from its stiffness to its transparency, to its color, to its conductivity. All manner of properties is described at a voxel level. So that an item can be fully described, and now think what happens to manufacturing. Now what I do is I design the product in a locale. I digitally send it anywhere I want in the world. It is localized in that area, personalized, changed, colorized, put in the right local environment, and with a push of a button, it is manufactured, it is printed out. That is the vision that we see in the next 30 years. Full digital manufacturing. When you can get to that, think about what happens with the city. No longer are you trying to ship massive amounts of products in or figure out how you disassemble them and get rid of the waste. What you're doing is you're manufacturing on demand, and you're manufacturing as you need it. So just as the internet today can spread instantly to other areas, and new applications that use the internet as a backbone show up around the world instantly, we see a world in which the physical products that we do can move at near that speed as well. That's what we call digital manufacturing. Now imagine what happens to the world when you get into a vision like that. Tax policy changes. How do you tax something when all you've done is sent the digital bits into the area? What is import? What is export? Policies change. Government regulations change. Where we manufacture changes. How societies are built changes. So over the next 30 years, we see there's going to be a complete industrial revolution into something new. Now, this is not made pie in the sky sort of a deal. It is happening today. So what we want to do is talk about the first footprints in the sand. And the first footprints is our multi-jet fusion printers. I'm going to lead it off. I'm going to give you a little video that talk about those printers specifically and what we rolled out. And then you're going to get a chance to talk to a couple folks. You're going to get a chance to see the gentleman who looks after all the 3D materials for our printer business. You're going to see the chief technologist and HP fellow who looks after the 3D business itself. And think about the questions you have as well, because we'll come back to the questions that you might have. But with that, let's talk about the product itself.
Tapping the potential of the smallest things has always led to giant leaps for humankind. So when we set out to reinvent 3D printing, we began at the molecular level with the smallest of building blocks, the mighty HP voxel, which led us to this, a leap beyond all the current limitations of 3D printing. Meet the HP Jet Fusion 3D printing solution. From this day forward, you will be able to reinvent the way you prototype and manufacture by creating consistently high quality and fully functional parts, up to 10 times faster, at the lowest cost. Continuous printing and fast cooling processes allow more production in the same day. From design to part, HP Jet Fusion 3D printing delivers an end-to-end solution that scales with your business. And the HP Multi-Jet Fusion Open Platform gives you access to a wider range of future materials and applications. Start reinventing the way you prototype and manufacture, voxel by voxel. HP Jet Fusion 3D printing. Keep reinventing.
So I'm a little bit like Chandrakant. I'm going to wander around a little bit while I talk. So I don't know if the title slide is up here, but you saw, my title is Global Head of 3D Materials and Advanced Applications. Really a better title is sort of head nerd, right? So that's how you should think of me. And yeah, there we go. So one of the cool things about being down here for this 50th anniversary today is I've been working for HP for 23 years next month. And in that entire 23 years, I've been working with folks down here at HP Labs and continue to, in Shane's team and Keith Moore's team. And so it's just fun to be able to be down here and kind of share a little bit. Not quite the full, half the time, but close. So Shane talked about the Industrial Revolution. The video just introduced HP's multi-jet fusion technology. I would contend that HP, together with the customers who buy a multi-jet fusion system and use our materials, are poised to take a huge step towards that next industrial revolution. And you might say, well, why, right? 3D printing's been around for 20, 25, almost 30 years, right? Why now is the industrial revolution, the vision that Shane was talking to, why is that going to occur? Well, let me talk a little bit about our value proposition and some of the things, strategies that we're going to put in place to enable that vision to basically occur over the next few years. First and foremost is we're leveraging our 2D inkjet technology to actually increase the speed by a factor of 10. If you look at most of the 3D printing today, it's basically a point process. There's a laser scanning back and forth, or there's a glue gun moving on an XY stage. It tends to be fairly slow. What we're able to do is take our thermal inkjet technology, all the intellectual property and the know-how and the ability to produce these at very low cost, and rather than a point standpoint, we actually scan this across the bed and actually jet down a fusing agent. We then scan a energy source which basically absorbs that energy and basically melts the plastic wherever that occur, but basically because of that we can get an order of magnitude improvement over anything else that's in the field today. Obviously, important as you start thinking about manufacturing. Another one is we're going to systematically drive material costs down. If you look at prototyping today, where maybe an engineer just wants to make sure that the part fits and it works and that he's designed it correctly and all matches up, typically he doesn't care too much about cost, right? But clearly if we're going to get into manufacturing, the Industrial Revolution, and compete with how the world economy works today for manufacturing, we're going to have to change that. And we're systematically going to bring the cost down on our materials. Another one is quality. The fact that we can bring speed and cost and quality at the same time means we're not just building a little part that's going to fall apart if you try to actually use it. Again, if it's prototyping, form, and fit, you just want to make sure it all fits together. It's not that important that it holds up. But if you're building something that's going into a car or a pair of shoes or an airplane, you have to have the material properties to basically enable that. And we're going to do that with our technology. The final part is we're going to bring the HP brand promise and quality and reliability to the hardware that we bring. And I work with my compatriots now across the globe to make sure that our product, when we introduce it later this year, will meet all those expectations that we've set with our customers for years. Another thing, when you look at manufacturing and think about how the world works today, we've learned a lot about this. If you look at all the different verticals, all the different OEMs, and look at how they say use injection molding, which is one of the primary ways we build plastic parts today, there's tens of thousands of materials. We were looking the other day, it's like 35,000 registered materials, right? And we're busy working on our materials, and we have, I'll talk about this a little bit more, a polyamide, a PA12. We're working on things like elastomers and so forth, but it came pretty clear to us, if we're going to scale this business, and scale it to the $12 trillion opportunity that Shane was talking about, we need to figure out how to get people to innovate on our platform. So we're bringing to the table an open materials platform where basically material companies can basically work the way they've always worked, working with their OEM partners in auto or aviation or consumer or tooling to basically develop materials, and then we'll certify it into our system. We have 4 pilots today that are working with us, 4 companies, BASF, Lehman Voss, Evonik, Arkema, actually working in our labs now as we speak. And the analogy I think of is Apple when they introduced their App Store in 2008. They basically brought that, and they had like 20 branded apps, right? And we have some branded materials today that we will have for a period of time. They had, a calendar, a weather app, a calculator, things like that. Right now, there's over 2 million apps, and people successfully run businesses. I was recently reading that so far the Apple app store has generated $50 billion of revenue, not just for Apple, but for the people who are using it. That is the analogy and our intent with our open materials platform. Instead of an SDK, a software development kit, we will have an MDK, a materials development kit, a printer where they can basically work to develop that material. And then just like Apple certifies that app into their system, we will certify that material into our system. The other thing we really need to drive is economics. We need to systematically figure out how not to just generate cool designs and so forth, but drive costs down. And through this open app store, we'll get a lot of new materials, and we expect costs to drive down. The thing I want to point out is for short-run production, we're already cheaper than analog production. I've got a couple parts here that I want to highlight. These were made with our multi-jet fusion technology on our printer. They're actual printer parts, right? And so the printer is printing itself, maybe half of the plastic parts, plus or minus. And it's not because we can print them, because it makes sense to print them. So let's think about this part here. If you're going to make an injection mold for this, that injection mold would probably cost $100,000, right? To basically make the mold to basically do this, not counting all the design efforts that basically go into that. If you build one part and say there's $1 worth of material in here, that part costs $100,001, right? If you build 1 million of them, it costs $1.10, right? I'm just doing simple math, right? So you have this sort of fixed volume curve, very consistent with our manufacturing world today. Well, for us to print this, let's say, I'm making these numbers up, by the way, don't quote me as these are numbers that are going into it, but say it costs us $10 to produce this, right, in our multi-jet fusion. It costs the same to make 1 or 10 or 100 or 1,000. So if you follow that sort of analogy I'm basically showing there, you could basically, the break-even point would be, for this hypothetical example, 10,000 parts between injection molding. So if you're building low-volume items, it already makes sense to use multi-jet fusion technology to actually move ahead and start to build that. Now, if you're building millions of these, you would basically want to jump over. So we call that bridge production on the sort of as a stepping stone in industrial manufacturing. So this part here, I think the break-even's about 500. This gear here, this is also a part from our printer. The break-even point for this gear is 50,000, right? And as we start to work ahead with our materials roadmap, we will systematically move that over the years from 50,000 to 100 to 1 million. So that's kind of a little bit about our value proposition and how we're going to get to the industrial revolution that Shane was talking about. At this point, I'll introduce my colleague and friend, Dr. Benning.
Thanks, Tim. So I am Paul Benning, and I'm I'm an HP fellow. Shane introduced me a little earlier, and the chief technologist for our 3D print business. I think if that makes you the head nerd, then I'd be the chief nerd. Is that the way we work those together? Thanks for that. So Tim did a great job talking about where we are today, essentially launching this 3D print business based on the technologies, this multi-jet fusion that he just described to us, using HP inkjet technology, so page-wide technology, and 2 liquid functional agents. So a fusing agent and a detailing agent to make these beautiful, highly functional plastic parts. What I'm going to talk about is where we go from here. Chief technology guy, I'm very worried about our current business, but a lot about the future. And the things I don't get to here, we'll get to see in Keith's lab on the tour later this afternoon. So you get another crack at some of these future technologies. And a lot of the things that I'm going to show you here were actually everything on this table. Started in HP Labs in the lab that you're going to see in a couple of hours, just in the other building. So that starts with the multi-jet fusion process itself and the black plastic parts that are in the multi-jet fusion printer today, and moves on to a series of things. So Shane mentioned voxels, Tim mentioned voxels, and we're able to print individual drops of functional agent on a 21 micron grid at every point on our build volume, and in X and Y, and then we're building that up layer by layer to build those voxels. And inside each one of those voxels, right now, we're printing black stuff or clear stuff to help us fuse things together and control the surface properties. In the future, and the work going on in the lab today, we'll print other things into those voxels in order to create many, many functional capabilities that I get to show you now. So the first thing that we'll bring out in our next generation of products is color.
So maybe not too surprising from the likes of HP that will bring full color capability. So black is nice, but people want more than black. So we'll do the full range. We'll bring cyan, magenta, yellow, and black, so process color to give 65,000 different shades of color into every part that we can print. So you can print individual, interesting colors, and you can print rainbows of colors in single parts. So that's because as we do the process, we're printing different drops in different voxels and giving us that color capability. So color sounds simple. We've been doing that for a long time in 2D on pieces of paper, but you might realize that just putting colorant on top of black plastic parts isn't going to make it very colorful. Maybe get a little color, but nothing as bright as this, and nothing as white as this. So the trick there is, if you heard Tim's description of the process, what we're doing is printing black things in, then what we're really doing is shining bright lights on it, so the black parts heat up and fuse together, and the parts that aren't black don't heat up and fuse together. And so if you want to make white parts, that's a conundrum. And so what's being invented is the ability to make fusing agents that aren't black, that are in fact clear or white. So you can have a white base that we build color parts on top of. So those are awesome in order to produce colorful, fun things, including figurines or models. So an interesting use case is for surgeons and others to print out real models of in this case, a heart that they may be operating on. So they can train themselves with the full color capability. You can see the shading. You can see what you have there, not just a single color model. And train up before you go in and cut people open and start working on real live people. So that's a great example of a functional use of color, but in a visual model. There are other applications of industrial use of color where, for example, we can print different colors at different layers. So we'd end up with wear indicators in a gear or in a rack. As you wear through that, exposing different colors would tell you how far you've worn through that part. So we have fully mechanically capable color parts, and then we have a couple of applications of just what that functional color can bring. And then, since we're entering into the era of digital manufacturing, another thing HP can bring with this color marking capability is uniquely identifying every part that's produced, marking that with a visible or an invisible code, and being able to track that part out into the wild. So as it's going through the rest of its life, you can check in, you could scan that part, understand what its current capability is, trace that back to its pedigree in the cloud, and eventually use all that data to close loop it back into the design process and the production process to make better and better parts. So those are some cool functional color capabilities. In addition to just color, as we move on, we're looking toward a future where the material properties, as Shane was mentioning, at every voxel can be varied. So this is a simple sort of toy example of a part that's both rigid on one end and then smoothly, finely graded to a more flexible region on the other end. And that's by printing different functional agents or different amounts of functional agent into different parts along this toy example part. You can imagine using that in more industrial applications. If you print things like elastomers, so gaskets, onto something that's, in this case, an ink receptacle that HP uses. So in addition to the unique design capabilities and the manufacture anywhere that 3D brings, now you're bringing multiple functional areas into a single part. So you're skipping whole parts of assembly at the end of manufacturing by printing those functionalities in one fell swoop. Maybe my favorite thing, and I'll close here on our voxel story, is being able to print electrically conductive materials and making conductive voxels within our plastic parts. So in this example, if you were paying attention at the very beginning, you saw a car lift video and a plastic chain link that we also have in the customer welcome center. And so that we lifted a car with a 4-ounce plastic chain link that was 3D printed with our multi-jet fusion technology. I think that's super cool. What we've done now is printed sensors and conductors directly into a chain link so you can also monitor the load as you're pulling that thing up. So what you can't see in here, but is in here, and we can electrically sense it, are traces that go together to make a strain gauge sensor. And so as we lift a load with that chain and deform it slightly, we can measure how much that load is. And that's just a simple initial example about what embedded sensors might do in a smart part future in an IoT-enabled world. I think I'll pause there. We have a lot more parts, and I could spend the next hour and a half talking about these things. But maybe we'll pause, and we'll bring Shane back up, and we'll take some questions from you guys and see if we're going in the right directions.
Come on up. You guys come in and take a seat. I have a couple questions first for our group, and then I want to see what questions you have as we think about the next industrial revolution. So the first one is we've shown a manner of different color parts, different capabilities you can print in, driven off of plastics and polymers. Tim, maybe you can comment a little bit about how you see material set expanding in the future and how we tend to grow that, and then maybe some of the unique materials that we can print today.
Yeah, so when we introduce here later this year, we'll have one material, but very quickly, rapidly expand that. So we'll have a polyamide, a PA12, which is probably most people are knowledgeable about if you've done any prototyping or engineering type work. We'll very quickly expand that into different types of additives, glass beads, fire retardant, different flavors of polyamides, different trade-offs. Ours will be highly recyclable. It's how we get half the cost. Our process, which maybe we can talk about later on the tour, enables a material that's less reactive than our competitors, so we get higher recyclability. But there might be other materials where you want to make different sorts of trade-offs. Exactly what I was talking about when you say a materials company works with their OEM provider. Different companies want different things. Later next year, we'll introduce some elastomers. This particular material here, we're looking at a couple different classes, kind of a classic elastomer, something you can use for a gasket or something like that. By the time we hit the end of next year, our pilot program on our open materials platform will start to, I think, greatly proliferate materials. And as we head into 2018, I expect to see a very large expansion of materials as we basically move ahead.
Now, some of the more interesting ones that we move out of plastics are some interesting areas in ceramics or in other areas. And without giving away the farm, maybe talk a little bit about how you see some of those revolutionary things happening. Either of you?
So those are certainly things that are being investigated inside HP, as you well know, and inside the labs. Our current product release is all about plastics. And then the addition of conductors, so that metallic capability inside those plastic parts. We've developed a ceramics technology that is world-beating, I'll say, and we're taking that out to the world to find great applications and partners and customers to help us develop that. On the metal side, we are bringing some of the same core voxel level capabilities to investigate what we can do long-term, I would say, in the metal space. Maybe the high-level statement is that we start with this multi-jet fusion, highly leveraged from our inkjet technology capability. And like in our 2D print business, don't expect that a single technology is going to do everything for us. And so as we look to the future of HP and 3D, we expect to go big in this space, and we'll end up with multiple technology vectors supporting that large 3D business. Excellent. Anything to add, Tim?
The thing I would add is if you go back to plastics, think about our inkjet technology. The fact that we own this inkjet technology, you're going to see some new products, page-wide products. We can actually just keep adding more print bars and more print bars. Our first product, as Paul mentioned, will have 2 agents, a fusing agent, a detailing agent. Down the road, we'll add color. Down the road, we'll have a conductive material that we basically add. We can start to add other things as well. So you can imagine building a People are often worried about electromagnetic shielding, right? So you can build shields around your parts. You might be worried about a part like this, but maybe one part of it interacts with another part. So you want to change the wear characteristics. So maybe we'd actually jet metal oxides into this or silica, so we can start to change the tribological effects. Paul already mentioned we can start to actually make this part elastic and this part stiff by jetting different materials in there. And Keith Moore's lab down here, and that team is doing some great work in that area. And so we'll start to see more and more agents start to show up, not just a breadth of materials, but the ability to engineer at the voxel level, which is really why we're coining the phrase digital manufacturing, because you'll be engineering at every single voxel, multiple material properties.
How about in terms of scalability? I mean, it's you see a set of parts up here, and I tend to carry a set of parts that will just happen to fit in my briefcase or bag, but how scalable is the technology? How do you see it scaling to larger form factors?
I'll take that one. So the beauty of having our graphics business and our 2D business, out here you see a new page-wide product. I forget what the product name is, but it's a series of nesting print heads like this. And we recently announced earlier this year a new web press, which I think is 3 meters wide, right? So 3 meters. We're able to stage that technology. Over time, we may be starting with...
For the Americans, you might have to translate that for 3 meters.
Yeah, let's see.
It's about 9 feet.
Yeah, thank you, Paul.
It's glad to help.
I spend so much time in Europe, I've lost track of the...
So Tim's bringing those analogies from the 2D print business and talking about how we can scale those print bars because they're at the core of multi-jet fusion. So we haven't yet, but we can bring that same print bar scalability into the 3D world and make print beds, 3D print beds as wide as those things. In theory, there's a little engineering work.
There's a little bit of engineering work. It's not quite on our roadmap yet. But if you think about, I talked about the competition and how 3D is done today with a point process, say a laser or a XY stage and a glue gun, that does not scale well as you get bigger. You have to put more and more lasers, and then basically the cost goes up in a nonlinear fashion. So we believe over time we'll be uniquely positioned to make large things.
And that's actually the hard dimension to scale in. And the other 2 dimensions, one is just scanning further with our print bar, and so that's actually an easier one to engineer. And then the third is the depth of the bed that we're building. So again, it's mostly mechanics. You just make a deeper bed, and you can build bigger parts in that dimension. So yeah, I think compared to all the technologies out there, to build things at speed, multi-jet fusion is the most scalable plastics technology.
So one other question, then we'll open it up for questions here in the audience is, in the vision as we move to digital manufacturing, it's not only the physical parts that we create, but it's also the supply chain that you're transforming and how you change the aspects of delivery. And we spoke about a vision that we call the Internet of All Things, where physical objects like tables or chairs or things that have no technology embedded in them can be uniquely tagged and tracked and associated with an internet service. Maybe you can talk to us a little bit about how you see 3D printing, digital manufacturing, how that can enable that.
Let me take a shot out, and Paul, you can clean up for me. I've spent 23 years at HP, and I've run a number of HP's factories, right? I've built, not run the factory that builds these, but up in Corvallis, Oregon, that builds a lot of our page-wide. And when you build a modern factory today, we track every single part. Incoming sand that goes into the silicon, all the way out to the internet-connected printer, and we track, the customer's usage. If he has a quality issue, we can sort of trace it all the way back and figure it out. Over time, with our technology, we'll need to do the same thing if we're really going to go into manufacturing, is the ability to track and trace. What we can do by adding another agent or a couple agents is we can add things that are very overt, just a colored label on the outside. But if you're worried about forensics and being more covert, we've played a lot with different types of fluorescent materials, quantum dots, where you can actually store information in a hyperspectral fashion through the whole part, right? So especially if you're building an airplane or something and you want to figure out what happened to that part, you can trace it all the way back in your factory. A little bit far out, but we've actually built it and demonstrated it. And so we'll build capabilities that frankly, ultimately our customers will be the ones that probably drive the need to have integrated factories and supply chain.
I think it's a really good description. I would just add, you gave a couple of examples, in our own inkjet print modules and in airplanes, where this is essentially done today. People, from point of manufacture all the way through the life of those parts are being tracked, either because they're high-tech things and we can, or because there's a lot of regulatory requirement in the case of the airplane. And what we can do with 3D print with HP's multi-jet fusion and our ability to do voxel level control is bring that capability down to the most mundane parts. So things that are relatively inexpensive, you bring that whole life cycle management, being able to track them out into the field, see how they perform, if they do break or when they fail at the end of their life, bring that information all the way back to the design cycle and make better parts that you then feed all the way through. And that's about the tracking of things and monitoring over the life of. Tim, you also mentioned the kind of covert and security aspect of things. So if people are doing brand management or if there's just security or safety issues with things, to be able to confirm that something in a secure environment, all the way from design to deployment in the field, is exactly the part you wanted, is another thing that we can bring.
Very good.
Yeah, well said.
Let's open it up and see what questions we have from the audience. Yeah.
Hi. First question for Tim. You mentioned that the cost of 3D printing is somewhere for the small part like 50,000 in industrial printing, or industrial manufacturing, basically. Do you foresee a future where 3D printing will be eventually be cheaper than industrial production?
Yeah, so first, I want to make sure I said it correctly. So the break-even point is 50,000 parts, versus it's not 50,000 euros or anything like that. But I think there's some cases where that's already the case, right? Because with 3D, not only are we driving a breadth of materials and driving a cost structure to enable manufacturing, 3D printing, as all of you know, you can make things that you can't make any other way, right? And so those parts, especially in the metals industry, are being built today because there is no other way. And at that point, if there's no other way, and you're trying to take weight out of the aircraft or something like that, it's already cost effective. Over time, as engineers and designers learn how to take advantage of 3D, I think people start to build more and more capability in. I showed this part coming out of our printer here. It's actually, previously, it was like 4 or 5 parts that have been all joined together. And every time you do that, you start to take cost out. Engineers start to think a little bit differently about that. And so over time, a breadth of materials, driving a cost structure that enables compared to manufacturing, and you're building things that can't be built any other way. So it's a long way of saying yes.
Well, it's a long way of saying that's already true for some things. So with that 50,000 part break-even point, it means that if you have an application, a need for 40,000 of those parts, it's already cheaper with multi-jet fusion to do that in 3D rather than doing it in traditional injection molding approaches.
Yeah, if we look at bigger, the question basically is there a future for big manufacturers, or will 3D printing basically wipe out the industrial manufacturing industry?
I always like to quote the Wealth of Nations, and going back to Shane's opening, right now what we do, it's all about access to raw materials, access to markets, right? And so we load a bunch of stuff up, we ship it somewhere, we make a part, and we ship it somewhere else. In the future, you'll be able to build what you want, where you want, when you need, and exactly how many you need. What that does to world manufacturers and economies remains to be seen. But that's why it's a revolution.
All right. Yeah. Thanks so much.
Absolutely. Other questions? Yeah.
A couple of questions. The price for this initial system I've seen for figures of about 150,000 and then 200,000 for the next thing. Obviously, with new technologies, the price goes up and as you develop the kit. But at what point will the traditional technology cycle kick in, the price start to come down again once the hardware's been standardized? And then on the materials side of things, HP's got a bit of trouble in the last couple of weeks with its 2D printing consumables. What's the situation going to be with 3D consumables? Will they all have to be HP certified and DRM'd as well?
Yeah, you want to try that? Take at least the first part. I'll take the second.
Yeah. So this is our first printer, our first platform, and we're making sure that we get it right. And sometimes that means building some cost in, right? You're basically building reliability. You're building quality. Of course, over time. I can imagine, just like our 2D printing business, I mean, going back, 25 years, you bought a DeskJet printer, which you can, get now for $49, I think was like $1,500, right? So things will come down over time, probably a classic learning curve. You can imagine that we will proliferate our portfolio over time as well.
If you look at where the world is today and the functional parts that are coming out and the throughput of the printers that we've announced and are selling now, those are already a step function, 10 times cheaper if you look at from a productivity standpoint. compared to what you can get on the market today. So $200,000 might sound expensive, but from a consumer printer standpoint, for sure. But on the scale of things, that's already way down the cost curve. And then everything Tim just said is, of course, true. There's the classic things we'll do around cost curves and our ability to engineer things. And I think there's a lot of room to invent on the multi-jet fusion platform, both for cost and capability.
And we mentioned at the outset that there are 4 big things with multi-jet fusion that change the game. 1, it's 10 times faster. 2, it's at a fraction of the cost. 3, it can manufacture parts, create parts that could never be created before because it operates at the voxel level. And then 4th, as Tim mentioned, it's an open system. And by an open system, what that means is we invite other folks to come in for materials that we can add into the printer itself. And actually, Tim has been leading some of those efforts here. 4 big manufacturers that we brought in.
Yeah, and you use the word certified, that's the way to think of it. Because actually, if you think about, we're basically passing an energy source over this fusing agent, which absorbs and melts it. I might have a material that melts at 150 degrees and another one that melts at 100 degrees. I got to certify to make sure that the whole thing doesn't, have events, right? And so we need to make sure we ensure the quality, the reliability, and so forth. And so we will, certify that. But it will be our partners' material, their brand. They will control the pricing.
Yeah, so it is very different from most of our 2D print businesses, I would say. You're correct, and it is a very different approach HP is taking.
Okay, other, yeah.
Well, what's the biggest shortfall you see in 3D printing? What's the one thing you're not figuring out?
Oh, good question.
Obviously, scale is a big thing. Or scale, I know you mentioned it, but where do you see the kind of the biggest problems or the biggest challenges?
Well, for us, I think the biggest challenges are actually the challenges we've laid out for ourselves, right? The example I would use, it's all about materials. This is not about printers. This is about selling parts to mechanical engineers and designers, right? Ultimately, they're going to design something that goes in this chair, your car, your microwave or what have you. They need a wide range of materials, right? They need a breadth of different things, so they all have different applications, right? And so the key behind creating this open materials platform, letting material companies innovate on our platform, and then we certify it in to create this breadth is what it's going to take for us to really penetrate and grow into this $1 trillion opportunity. Now, that's not, you could say, well, it's not a shortfall because it's our strategy, but we need to execute to that, learn how to do that, and set the whole world up to basically participate.
And we've definitely set, especially our technology strategy, around all these things, all the things that we see as issues, and they maybe are shortfalls, maybe they worry us, but those are really fun problems to work on from a technologist perspective. I think the thing that seems less in my control anyway, I'll just speak for myself instead of all HP, is the cultural shift necessary in design environments to get people, designers, thinking about designing in 3D. So if you think of plastic parts, designers, we have a lot of these inside HP too, they start already knowing a lot about the limitations of injection molding and sort of modifying their designs in their heads even before they start putting, mouse to screen in order to design it. And so getting that, that cultural shift, getting people to think differently and design into 3D capabilities, the strength of 3D, is maybe going to be the longest lead time item. Cultural changes don't come overnight. And maybe you can help us all with that.
Is it on?
Yeah.
Hi. Is it bringing your 3D printing technology to a consumer space is something that you'd look into in the future, or you would just stick to the digital manufacturing?
Yeah, I can comment on it. Is if you look at the market today, the thing that created the hype that everybody was excited about was the desktop printer, right, or the home printer. And the reality is, if you look at the market, 95% of the value in the market, of the revenue and the profit, sits in the enterprise, the commercial area, and very little, that sits in the consumer side. So maybe eventually it gets there, but I actually think the more realistic model that's going to create, fully functional items is one in which you see. Today in the 2D world, we have what are called print service providers, or PSPs, which are local. Think of a Kinko's or somewhere where you would go and print out things. But that being in 3D. So that what you have are these shops that are, and we have them already around the world that have a set of 3D capabilities. And so then the motion becomes, you sit at home, I need a new case for my phone, whatever it is. You find the digital representation of it, you change it, personalize it, put your name on it, you hit, send to me. It prints out at that local 3D print service provider and is mailed to you and lands at your place in 2 days, or whatever it might happen to be. So I think that's probably in the short term going to be the model. You're still going to have some of the local home printers, but I think the cost and the functionality will be low cost but limited functionality. Okay, time for one more. Yeah.
Okay, thank you. The speed of innovation is very high in this area, and maybe in 1 year's time you will present right here another printer from HP will be, 100 times faster than this one. So do you have any ideas for early adopters of your technology, how to protect their investment in this product, some upgradability or trade-in or whatever?
Why don't we answer that in short and long term? Maybe talk about the support model in the short term and how you see that advancing a little bit, and then we can talk about longer term.
Yeah, so it's a great question because I think you're spot on. I mean, we're already showing things that we've demonstrated in the lab and so forth. So you can imagine doing that, and so making sure that we're coming out with products that have that longevity. We've talked about upgradability from a hardware standpoint. In the short term, we probably aren't able to do that just because of the limitations. But absolutely, what we're learning is that we can probably end up having, we can start to make some of the trade-offs in the printer itself relative to speed, relative to part quality, and so forth. And doing sort of upgrades and so forth is probably something we can do for the first product. For quite some time, and then we get to the
there's maybe a couple of flavors of that answer. The literal upgrade kits for hardware, you need to do the economic balance at a $150,000 machine. Maybe there would be really limited things, but you don't want to spend $150,000 on an upgrade kit for your $150,000 printer. On the other hand, new materials and new functional agents will definitely lean on bringing the entire library of materials that get released into the multi-jet fusion environment to the very first printer, to the first printer that's already out there now. So things might break in the future where the capability isn't there, but as much as possible, we'll keep that solid on the roadmap. And then the same with functional agents. As we can add, as we can bring more technology into the functional agents, we'd look to bring those into existing printers. But the pace of innovation is going to be rapid, so there'll be new products that bring all the capabilities for sure.
Longer term, so we'll come back and wrap it up here from a longer term standpoint to address your question is what we're talking about is a vision, a 30-year vision. And that vision is how do you change manufacturing to be much more responsive, much quicker in order to bring products to market and to do it in a lower waste fashion. And to address really the biggest issues when we talk about the mega trends of where society is going. So to deal with product delivery in a rapid fashion in highly dense environments. To have things move at near internet pace in order to further hyperglobalization. That's what the vision we're aiming at. So now think about it within the context of even the question that you ask, which is today we can do these things. Tomorrow we're going to be able to add more properties and we're going to be able to add more electronics in. That's only a couple years out. Imagine what happens over the next 30 years when suddenly the amount of material, the types of products you can produce, how you can mix them together, how you can have a combination of electronics and plastics that can go into parts themselves, how supply chains transform. And now I have the ability for things to move in a digital fashion from end to end. What manufacturing will look like will be radically different in that 30-year time frame than what we see today with our stodgy smokestack done in emerging geography world. It will definitely be a world that addresses the needs of megatrends. Okay, with that, I think we're going to wrap here. I'm checking. Thank you guys very much.
Thank you.
Yep, good.